Hi, I'm Hao Dai. Today, I'm going to present our work modeling the shape of the brain connectomes via deep neural networks. This is a collaboration work between me, Martin Bauer, Tom Fletcher, and Saran Joshi. So, what is brain connectomes? The brain connectomes is where our memory, personality, and intelligence encoded in. It is the connections reside in the white matter of the brain that connects different regions of the gray matter. The fiber tract we saw here is namely the connectomes. Structure connectivities tells you the physical existence of the white matter tracts, which interconnects different parts of the brain. It is important because the structure and the function of the human brains are interlinked. The foundation of the human cognitions lies in the pattern of the interactions shaped by the connectomes. And we use tractography to represent the structure connectivities. It can be any method to estimate the trajectory of the fiber tracts in the white matter. Then, how do we infer the tractography? Diffusion-weighted MRI has been extensively used to study the brain connections and measure the diffusion of the water molecules, which will be largely constrained by the direction of the neurons. Once we have the diffusion MRI, we can infer a vector field through a lot of modern techniques, such as Hardy, Q-ball, and DSI. These vector fields will serve as the tangent vectors of the tractography. Then, by using the deterministic or probabilistic tractography, we can have the final representation of the human connectomes. But here comes the question. What if we want to statistically analyze a population of the connectomes? Neither deterministic nor probabilistic tractography can offer us a solution. Luckily, constructing a Riemannian manifold for the connectomes is a very ideal tool for later statistical analysis. There are a lot of tools we can utilize to calculate an average brain connectomes, which quantifies the geometric variabilities over a population. And geodesic tractography is a method endeavored to estimate the Riemannian manifold, such that the geodesic paths follow the given tractography precisely. The right figure is the visualization of the Riemannian matrix. Black line represent the tractography, and the indigo line represent the geodesics. If the geodesic matches the given tractography perfectly, then we can call this manifold is a good one. In the previous work of Adorno et al., they took the inverse of the diffusion tensor as the metric tensor. The rationale behind it is that as we move in the major axis of the diffusion tensor, the time cost is low. As we move in the minor axis of the diffusion tensor, the cost is high. So it aligns with our goal. The pros of the geodesic tractography include enable us to find the tracks between two endpoints, and it is the perfect tool for the study of the brain geometry. But what's the problem of the previous geodesic tractography method? As we can see in the right panel, the magenta geodesic using the inverse tensor field as the metric could not follow the blue tractography. And the red shortest path under the Euclidean metric is also far from the ground truth. The previous methods are also not designed for characterizing crossing fibers, which widely exist in human brains. The foundation of the geodesic tractography is the Riemannian matrix. It basically tells us how to calculate in the product under a given space. Then, we can calculate the length from one point to another by integrations. In the Euclidean space, the metric is the identity matrix. In a Riemannian manifold, it can be any symmetric positive definite matrix. The ellipsoid on the right-hand side demonstrates how we visualize the metric tensor. The shorter the axis is, the lower the cost it travels. The lengths and the directions of the axis correspond to the eigenvalues and the eigenvectors of the metric. So what is geodesic? Geodesic is the path that locally minimizes the length between 2 points. Besides this property, the speed of the geodesic on the Riemannian manifold is also constant. That means the tangential acceleration of the geodesic is 0. If we want to compute geodesic curves, we need to find curves where the acceleration vector is normal to the space. Namely, nabla gamma dot equals to 0 holds along the curve, where the nabla is called covariant derivative, or the Levi-Civita connections. So what is a covariant derivative? It tells us the rate of change vectors at u of the vector field in the direction of w. It is the generalization of the directional derivative and provides connections between the tangent space in the curve space. Explicitly, covariant derivative nabla GVV can be written as the equation 4. A vector field V is called the geodesic vector field if and only if it satisfies nabla GVV equals to 0. For unit speed geodesic, the nabla GVV equals to sigma V. For non-unit geodesic speed geodesic, where the sigma is the scalar, can be calculated by these equations. As shown by Spivak, a critical curve for unit speed geodesic equation 1 is also the critical curve for equation 2, which is a non-unit speed geodesic. The only difference is that the geodesic that minimizes 1 has a constant speed. When we interpret it in a covariant derivative way, for non-unit speed geodesic, it means there's no restrictions on the norm of the geodesic vector field. So it is equivalent to making the nabla V norm V equals to 0. Then we can have the expression of the sigma. So here comes the bigger picture of our work. We first try to get the tangent vector of the Tractography from the diffusion tensor image. You can also use any state-of-art Tractography method to get the B. Here, we perform the eigen decomposition of the diffusion tensor to achieve this goal. Once the tangent vector field is given, we enter the stage of the metric estimation via the deep neural network. Given the vector field living in the manifold M, our objective becomes to find the Riemannian metric G on M that minimizes the energy functional. The summation allows us to have the metric to accommodate multiple tangent vector fields, which essentially represent low crossing fibers, and the regularization term is also added to prevent overfitting. To solve this objective function, physics-informed neural networks, abbreviated as PINs, is the best candidate to help. It leverages the universal approximation ability to deep neural networks to estimate the solution of the PDE by encoding the inverse problem into the loss function. The automatic differentiation module embedded in most machine learning frameworks, such as PyTorch and TensorFlow, automates the process of finding the solutions efficiently and matchfully. In the first stage, we adopt the multi-layer perceptrons as the architectures. We sample tens of thousands points over the geodesic vector field, sending the spatial coordinate into the network. The network will then generate a 7-dimensional vector, serving as the distinct entries for later matrix constructions. We leverage the eigen composition and the Rodriguez rotation formula to turn these 7 entries to a 3x3 symmetric positive definite matrix, which is the final metric tensor at the corresponding location. In order to calculate the objective function, we need the vector field itself, which is given, and derivative of the vector field regarding the spatial coordinate, which can be derived by the central finite difference, and also the derivative of the metric with respect to the spatial coordinate, which can be derived by the autograd. However, we found severe limitations of MLPs in our experiment. The predictive abilities and the accuracy of the MLPs decays drastically as the dimension and the complexity of the solution increased. To overcome the inherent limitations of the vanilla MLPs, we switched to use a convolutional encoder-decoder neural networks approach to construct the multi-scale features from high-dimensional input. The main workflow is analogous to preventing previous formulations, except that at this time we're sending the whole vector field into the CNN, concatenated by multiple vector fields describe the crossing fibers, and the output is a 7-channel 3D volumes. Then we use these 7 channels to construct a 3D matrix field. It is the final estimated metric which can accommodate multiple crossing fibers. Since the input of the network is no longer spatial coordinates, the derivative of the metric can no longer be derived by the autograd. Likewise, we adopt the central finite difference to get the derivative. Hence, all the ingredients of the objective function are ready, and the network can learn the mapping from the vector field to the Riemannian manifold by optimizing the objective function. To construct a symmetric positive definite matrix, we initially used a matrix exponential strategy. The new eigenvalues will basically be the exponential of the original one, which guarantees the positive definiteness. However, we find that the backpropagation of the matrix exponential is the bottleneck of the training process. We then switch to an eigencomposition strategy to construct the symmetric positive definite matrix from the 7 entries, which needs to a diagonal matrix, an orthogonal matrix, follows the Rodriguez rotation formula. This formulation expedites the training speed by 5-fold compared to the building torch matrix exponential. Once the estimated Riemannian metric is ready, we need to run the geodesic to verify whether the metric is a good one. We choose the starting point and the initial shooting directions at the red dot and the gray arrow indicate. Then we iteratively march forward, calculating the acceleration via geodesic equation, updating the velocity at the new point, so on and so forth. We can derive a geodesic. In our first experiment, we compared the geodesic tractography alignment of both previous and our new method. The inverted means it takes the inverse of the diffusion tensor as the metric. The aggregate means it takes the aggregate of the diffusion tensor as the metric. And the conformal means it applies scalar field modulations to the inverted diffusion tensor. To quantitatively measure the alignment over this method, we test these algorithms on brain slices from 38 HCP brain connectomes, brain subjects. On each brain slices, we uniformly cast 400 seed points in the genu of the corpus callosum region. At the seed point that chosen to be non-grid points with the corresponding vector being obtained by the bilinear interpolation. In other words, these vectors have never been seen by the network. As you can see in the visualization, the background is the tangent vector of the tractography representing the water diffusions. Both the black tractography and the colorful geodesics are shooting from the black star in the same directions. Yellow, red, green, and the indigo curves represent the geodesic running on the inverted, aggregate, conformal, and our metric. It is very clear that our geodesic characterize the tractography most precisely, while all the other geodesic deviate from the tractography at the end of the day. To calculate the distance between the two curves, we will P and Q as a finite point set. We consider mean error between these two sets by shown equations. P denotes the tractography and the Q denotes the geodesic tractography curve starting at the same seed point. The box plot visualized the distribution of the 15,000 arrows across 38 HCV subjects. The box plot demonstrates that our method outperforms other three methods in terms of both mean and median of the arrows by a large margin. There are more examples demonstrating our method advantage over the previous one. On the bottom is the brain subject ID. To test the ability of characterizing crossing fibers, we synthesized two vector fields in the Braid pattern of two intertwining pathways. The metric field GP and GC estimated by MLP and CEDNN as shown on the right-hand side. Both the baseline MLP and the CEDNN use around 0.7 million parameters. The geodesic on the metric GC align notably closer to the tractography than the one on the GP. In addition to the excellent geodesic tractography alignment, the CEDNN estimated the metric behaves as expected even as the crossing region. The geodesic are not confounded at all. In addition, we configure the MLPs with the Fourier embeddings in the siren activation function, which boosts the performance of the MLP in a considerable magnitude. Yet still underperforming the CEDNN by orders of magnitude. It is noticeable that the CEDNN converges much faster to a significant lower residual loss, despite the fact that the MLP enjoys about the same amount of parameters as the CEDNN. We also validate our method abilities of the 3D crossing fiber regions in the brain DWI from the several HCP subjects. We first reconstruct the vector fields through the GQI method in DSI Studio with the diffusion sampling length ratio of 1.25. And whole brain Riemannian matrix was estimated by the CEDNN featuring 40, 30, and 40 dense layers in each dense blocks. And it took less than 30 minutes, 10,000 iterations for convergence of a single NVIDIA Titan RTX GPU. There were 138,000 seed points cast in the white matter region for the generation of the geodesic. We showcase the abilities of the geodesic tractography with our estimated metric to successfully distinguish two crossing fibers, the full-step minor and the frontal projection tracts. We suggest that the previous approach to geodesic tractography do not handle multiple fiber directions in the voxel, and thus cannot correctly handle the crossing fiber regions such as these. So in this work, for the first time, the deep neural networks is used to estimate the Riemannian metric to characterize the human connectomes. Our proposed method outperforms any of the previous geodesic tractography method by a large margin. And the long-standing problem of the inability to recover the crossing fiber is also overcome by other methods. However, our method needs to solve from scratch for each new coming brains. Though it only takes half an hour to convert, it is still in our hope that the generalization ability can be strengthened in the future. With the ability to robustly and efficiently model the brain connectomes as the Riemannian manifold, one can directly apply the geometric statistical techniques such as statistical atlas construction, principal geodesic analysis, and longitudinal regression to precisely study the variabilities and differences in white matter architectures. If you are interested in our work, please scan the QR code to find more details in our project page. Thank you.